Net ionic equation lab, and we're going to look at single displacement reactions and how to do those. So I'm going to bring this up and get a little marker. And most of the things you've seen have been double replacement. We use the solubility table to figure things out. But also when I get to number 7, I got a single replacement. And number 8 and 9 are single replacement reactions. So how do we do those? I'm going to go to the very last page where I demonstrate a few of those. So I'm going to call those redox reactions, sometimes called for reduction, oxidation. And what does that mean? Things are reduced when they gain electrons, things are oxidized when they lose electrons, but it's things gaining and losing electrons. And we'll kind of see this in this process right here. Take an old standby right here. I don't know if you can see this right up here. I have the I had a copper wire and I put it in silver nitrate. So we did this back in the fall. And then what happened? We formed silver on here, and then this clear silver nitrate solution changed to copper nitrate, and that turned blue. So kind of going back to that one reaction again, and that would be the single displacement reaction we're seeing right here. So how do we write a net ionic equation for that? Let's balance it first. We have copper as a solid, because that was a copper wire. We had aqueous silver nitrate, so we had silver nitrate crystals dissolved in water. Ag is +1, NO3 is -1, so that's balanced formula there. We formed copper 2 nitrate, so it just so happens to be copper 2 nitrate. That's the blue color. Copper is +2, nitrate's -1, therefore it's CuNO3 2. And then the stuff was on there is silver. And remember, we dried that. That is a solid. Okay, so the middle two are aqueous, and then what the copper and the silver are solids. This one the reactant, this one the product. Okay, so let's say we're writing a net ionic for that. We can't do anything with copper as a solid. We can't do anything with silver as a solid, but the aqueous things we split up into ions. Okay, so I'll split my 2AgNO3 into 2Ag plus and 2NO3 minus. I'll split my CuNO3 into Cu +2 plus 2NO3 minus. That becomes my total ionic equation. And then what's identical in each one? The nitrates, so they cancel out. So the net ionic equation becomes Cu plus 2Ag plus from Cu +2 plus 2Ag. Now, isn't Cu and Cu +2 the same thing? No, this is a solid piece of metal, but it gained electrons to become what? Cu +2 in this solution. And this Ag plus that was in solution becomes just the metal as the element in the solid state. So by writing this, it's a shorthand, even without the subscripts, saying, hey, if this has a charge on it, okay, what's happening is, why does it have a charge? Because it's in an ion in solution. These don't have charges of copper and silver because they're actually elements in their free state. Notice what's happening. Copper is going from 0 charge in its free state to +2. So it actually lost negative charge. It lost electrons to do that. And silver gained electrons in order for that to happen. Now, what if let's just take a look at the table to make sure this is a no reaction. So I'm going to look at my activity series, which is right here. Remember, the ones toward the top of the list are more reactive toward the bottom than toward the bottom. So notice I have copper. Oh, that's pretty low on the list, but not as low as silver. Okay, so copper will lose electrons more readily than silver. So let's see if this is the case for what we have. Copper, did it lose electrons? Yes, it went from Cu to Cu +2. So copper will replace silver in this reaction. If I try to put silver plus copper nitrate, because silver is below copper on the activity series, I would get a no reaction. But I do get a reaction here because copper is more reactive or loses its electrons more readily than silver. Here's another example. And we just did this lab where we took magnesium and hydrochloric acid for magnesium chloride and hydrogen. There's a balanced equation. We did this and collected the gas in the tube in the eudiometer. Okay, And I'm just going to write the total ionic equation. I'm going to take my HCl and break it into 2H plus and 2Cl minus. I'm going to take the Mg and break it up into MgCl2 and break it up into Mg plus 2Cl minus. Okay, what's my spectator ion? It's the Cl minus. Okay, and what am I left with? Mg going to Mg plus 2, losing electrons, and H plus going to hydrogen gas. Oh, remember we collected a gas and that's what was formed there. So the magnesium is losing the electrons. The hydrogen is gaining the electrons here. Does that happen according to the activity series? Does magnesium lose electrons more readily than hydrogen? I'll go to that activity series and see, okay, even though there's all metals here, we see magnesium. Whoa, where is that? Pretty high up here. There's magnesium up here, and there's hydrogen below it. So displacement of H plus in acids is what we have, okay, with this reaction. And yes, magnesium, up here, would replace the hydrogen in hydrochloric acid, giving us this reaction that we see here, but still a single displacement reaction. All right, there are some single displacement opportunities for 7, 8, and 9, I believe, in that lab. Good luck. Thank you.